We're going to pull back the curtain on a secret of light, one that pretty much makes the entire modern internet possible. It's all about creating a flawless reflection, a perfect trap for light. But how on earth do you make a perfect mirror without any silver or polish?
We all learn in school that light travels in straight lines. So, what is happening here? This laser beam looks like it's trapped, bouncing perfectly inside a simple sheet of glass. Now, this isn't some camera trick. It's a fundamental principle of physics at work, turning a totally normal material into a flawless guide for light.
So, how do you do it? How do you build that perfect pipe for light? Well, to answer that, we first have to understand a basic rule about how light behaves when it crosses from one thing into another. Because you see, it doesn't always go straight, and that's where things start to get really interesting.
So, let's talk about bending and bouncing. Because to trap light, you first have to know how to bend it. The first rule is, well, it doesn't always play by the rules we think it does. You've seen this a million times. You put a straw in a glass of water, and it looks broken, right? That bending is called refraction. It happens because light actually changes speed as it moves through different materials, and when it crosses that border, it has to change direction.
Now, the direction of that bend is absolutely crucial. Physicists measure it against this imaginary line they call the normal, which is just a line drawn at a right angle to the surface. So, when light enters a denser material, like going from air into water, it slows down and bends towards the normal. But, and this is the important part, when it goes from that dense water back into the rarer air, it speeds up and bends away from the normal. That simple act of bending away is the key to everything.
Okay, so what happens if we keep pushing that angle? When the light is trying to escape and bending away, well, that leads to a really remarkable tipping point. So, picture this. You're underwater with a flashlight, and you point it up toward the surface. At a shallow angle, no problem. The light ray shoots out into the air, bending away from our imaginary normal line as it goes. But as you start to tilt that flashlight up, increasing the angle, the escaping light ray has to bend more and more sharply. Eventually, you hit this magical tipping point. It's called the critical angle. And right at that exact angle, the light doesn't really escape at all. It just skims perfectly along the surface of the water. And here is where the magic happens. If you go just a fraction of a degree past that critical angle, bam, the light cannot escape. It's physically impossible. The surface has suddenly become a perfect mirror. 100% of that light is trapped, reflecting perfectly back down into the water. And that is total internal reflection, or TIR for short. We're talking about a flawless reflection with absolutely no loss of light or brightness. It's way, way more efficient than any silvered mirror you could ever make. And remember, it only happens when light is trying to go from a denser place to a less dense one. And here's the cool thing. Every material has its own unique critical angle. For water, you need to hit the surface at more than 49 degrees to trap the light. For glass, it's a little less, around 42 degrees. But look at diamond. It's so optically dense that its critical angle is tiny, just 24.5 degrees. That's the secret to its sparkle, by the way. It's just incredibly easy to trap light inside a diamond. Now, this isn't just some neat physics trick you see in a lab. This one single principle is literally everywhere, powering everything from the internet you're using right now to the sparkle in a gemstone. So let's go back to our first question. How do you build a pipe for light? This is it. Fiber optic cables. They're super thin strands of glass, and we shoot pulses of laser light down them, carrying all our data. Every time a pulse hits the inner wall of the fiber, it does so at an angle greater than the critical angle, and TIR forces it to bounce perfectly, again and again and again, for thousands of kilometers. It's also why diamonds are so breathtaking. They're not just sparkly rocks, they're perfectly engineered light traps. The facets are cut at very precise angles so that any light that gets in through the top is bounced around inside multiple times by total internal reflection before it's fired right back out the top, creating that brilliant flash. You'll also find it inside high-quality binoculars and cameras. Instead of using mirrors, which can get dirty or misaligned, they use solid glass prisms. The light path is folded inside the prism using perfectly efficient total internal reflection, giving you a super clear, bright image in a really compact device. And you've probably seen this yourself. It creates that shimmering, perfect mirror on the surface of a swimming pool when you're looking up from underwater. If you look straight up, you see the sky. But if you look at the surface a bit further away, beyond that critical angle, you see a perfect reflection of the bottom of the pool.
Okay, so it's a total reflection. It's perfect, right? Well, what if I told you that's not the whole story? There's one more very strange twist to this tale. Get this. Even when total internal reflection is happening, a tiny ghost of the light actually leaks out a minuscule distance into the other medium. Scientists call it an evanescent wave. It doesn't carry away any energy, so the reflection is still total, but it's there, hovering just on the other side of the boundary. Now here's where it gets really weird. If you bring another object, like your fingertip, close enough to actually touch that ghostly wave, something amazing happens. The ridges of your fingerprint interact with that evanescent field and basically give the light an escape route. You frustrate the reflection, stealing the light away. This is called frustrated total internal reflection. And wherever your finger makes contact, that perfect mirror just vanishes. This strange, ghostly effect isn't just a cool party trick, it's a real, visible glimpse into the absolutely bizarre world of quantum mechanics. It's a large-scale version of a phenomenon called quantum tunneling, where tiny particles can pass through solid barriers that they should, by all classical logic, never be able to cross. It's a wild reminder that the weird rules of the quantum universe are at play all around us. So think about where we went. We started with a simple observation: light bends in water. And from there, we got to the technology that powers global communication, the brilliance of a diamond, and even a peek into the quantum realm. It just goes to show how understanding one simple secret about the universe can completely reshape our world. Which really makes you wonder, what's the next impossible thing we can do with light?